So good afternoon, everyone. Welcome back to Math 122. And what's your name start with?
D.
Sorry?
Starts with D.
I hope it's not Daniel. It's Drew, right?
Yeah.
Okay. I knew Drew was coming at some point. That would have been 4 Daniels in the class. That would have been just too many. Okay, let me set an alarm. We're going to have the quiz at the end of class, so I'm going to set my alarm for we end at 4:05. So I'm going to set my alarm for 3:48, and that's when I'll pass out the quizzes, and then you'll take the quizzes at that time. And I forget your name, too. What is your name?
What's up?
What's your name again?
Ryan.
Ryan. Okay. I'm almost there. I think next week probably I can have everybody down. All right. So like I said, welcome back to Math 122. Today we're going to try to talk over 2 sections, which means we're going to pick up the pace just a little bit. So today, I apologize. It's going to be a little bit more of me talking and a little bit less of you doing group work. I don't like to do that, but the first chapter is like a lot of just kind of terminology and review that we have to get through. So we're going to go a little bit faster today. But if I'm going a little too fast, just raise your hand, ask a question, slow me down, whatever, okay? Regarding homework, you had 1.1 was due already. 1.2 is due tonight, okay, at 11:59 p.m. So that's when 1.2 homework is due. Your next assessment is today. That's quiz 1, and it covers the questions from homework 1.1. So the quiz questions come word for word from the homework. So that's what you should study if you want to study for assessments. My office hours are 11:30 to 1. For the time being, I'm gonna change one of them though at some point. But I haven't figured that out yet. And then Math Tutoring Center is the other place you can go to get math help. That should be up and running starting Monday. Yeah, go there and talk with other graduate students, or you can check for the schedule to see when I'm there. I'll announce when I'm there once I get the final schedule. So that's administrative stuff. Any administrative related questions before we start class today? I keep forgetting to email them. I mean, I would imagine that other people are complaining. That's probably why they put these fans in here. Yeah, it is kind of annoyingly warm in here. Sorry about that. Any other questions? All right. Then let's review what we talked about last time before we move on to something new. So last time we talked about linear functions and the slope of linear functions, how to identify whether a function is linear or not. Remember, that was they're characterized by this sort of constant rate of change. They go up by an amount which is proportional to the amount they go over, right? That's why we have the slope is the rise over the run. Okay, so we also had some basic interpretation. Okay, finding the equation of a line given 2 points. That's a really important skill for this class. And that was pretty much it. But we have this other problem, which I was going to do as a group work problem, but I'd rather have you try this one on your own at home. I don't think that you'll need a partner to be able to do it. But it's good practice to ask yourselves, okay, when do we have a positive slope, negative slope? The only ones I want to highlight is what kind of slope do I have if I have a horizontal line?
0.
0, right? Because we have no rise and all run. Okay? And what about a vertical line? What's the deal with vertical line slope?
1.
Not 1. 1 would be if we go up 1 over 1, up 1 over 1, up 1 over 1. It'd look like this.
Is it undefined?
It is undefined. And here's why. If you think about a vertical line, take 2 points on this vertical line. What's the rise? The rise is however much you rose, right? So that'd be like rise is, I don't know, this looks like 4 or something like that. And what's the run?
0. 0.
0. So now you see the problem, right? 4 divided by 0. We can't do that, all right? So that's vertical lines. So the only other thing I wanted to quickly touch on before we move on to the new section was regarding how many times lines intersect, okay? And basically there's 3 different situations. The first situation is for 2 lines to have a different slope, in which case they touch each other exactly 1 time. So different slope, different y-intercept, we're going to cross 1 time. Different slope, same y-intercept. The y-intercept is kind of irrelevant here. If they have a different slope, they're going to cross exactly 1 time. And then what do we have? We have the other cases. We could have parallel lines. What's the relationship between the slope of 2 parallel lines?
They're the same.
They're the same. So if they have the same slope but a different y-intercept, okay, like shown here, okay, same slope but different y-intercept, meaning these 2 heights are different, how many times are they going to cross? 0 times. Okay, and, oh, whoops, meant to put that here. And what about if they have the same slope but the same y-intercept? Then here's line number 1, and line number 2 is like right on top of it, right? So in this case, we have infinitely many intersections. Oops, that's 0. Here's infinity. Okay, so that was basically the other thing I wanted to discuss. So any questions on lines, slopes of lines, point slope form, finding the slope, or finding the equation of a line that passes through 2 given points? All right, if not, then let's move on to today's material. Do I want to talk about that? No, I don't care about that. Let's move on to today's material. So, we're going to have a definition, and then I'll show you an example, and then we'll do a little bit of group work, okay? So, one of the fundamental concepts in calculus is understanding rates of change, right? So think quantities like miles per hour or dollars per unit sold, okay? We want to understand how these things are changed, okay? In fact, calculus could be rephrased as like the study of change, okay? The study of rates of change and of accumulated change over time, okay? That's basically what calculus is about. So the only rate of change which we've talked about so far is the slope of a line, right? The slope of a line tells us how quickly something is going to rise with respect to something else, right? So if we have a very steep line, so let's draw an example here. Let's have, how about P being profit and Q being units sold, right? Maybe initially our profit is like not very much because we have to make an initial investment, but then we make a certain amount of money for every unit that we sell, and this is what our profit function looks like. Well, how steep that profit function is going to tell us how much profit we're earning per unit sold, right? That's basically what this is going to tell us. So average rate of change is a way of sort of extending this notion of change to a wider class of functions, because right now we only know how to explain what is the rate of change of a line, right? But we know there's all sorts of other kooky functions out there which might look different. They might be curvy looking functions or something like that. So what is average rate of change? Well, average rate of change says that, okay, the average rate of change of f of x over the interval a comma b is given by f of b In fact, why don't I write AROC, that's usually how I abbreviate average rate of change, is equal to F evaluated at B minus F evaluated at A divided by B minus A. And let me pause and ask, does this quotient look familiar at all based on what we've studied so far? I'm seeing lots of heads shaking yes. Alex?
When we find the slope.
Yeah, this looks like a slope, right? y2 minus y1 over x2 minus x1. But let's see why this is a little bit different when we're talking about curvy functions than it is when we're talking about a line. At a line, you just pick whatever b or whatever a you want, and you're going to get the slope, right? You're going to get the slope of that line. But if we have instead, allow me to do a drawing here. If we have instead a function which is curvy, so let me draw one that looks like this maybe. And let's say here is A, and here's B. Okay? Remember, A and B are going to be our x values because we're talking about interval. Interval is going to refer to, of course, the domain of this function, i.e. the values which the independent variable can take. Okay, so A and B are shown here. What about f of B and f of A? What are they?
Is it the point on the line?
It-
Where we're gonna go?
They're going to be points on this curve, actually, right? Well, but they're going to specifically, the A and the B refer to the x value of the points on this curve. But the f of B and the f of A refer to what? The y values, right? So you could list them if you want. Here is f of A, and here's f of B is somewhere up here. Or if you want, you could go to these points and say, this is the point A comma f of A, right? Because that's how we get the height of the function. We take the input and we plug it into the function. Whatever the output is, that's what we make the height of the function. Okay, and likewise over here we've got B comma f of B. Then, this quantity is the slope of a line. Which line is it? The slope of. I don't see any lines on my graph here other than the axes. Yeah, the line that goes from A comma f of A to B comma f of B, we could draw in, would look like this, right? Okay, so now we have a line, and this is very clearly the slope of this red line here. Okay, it's very clearly the slope of that red line. Okay, and what does it mean when we say that it's the average rate of change? It says, well, look, if you were to say, take a lot of the points here and just take, okay, how should I do this? If you were to take a look at the slopes of various segments of this thing, right? Various segments of this curve here, and average them all, meaning add them all up, divide by how many there are, right? Then the average slope of this curve between A and B is going to be the same as the slope of this red line, okay? Kind of describes how this function is changing on average for this period of time. Here's another way to think about it. If this blue curve, whoops, if this blue curve is distance from home, okay? So initially I'm somewhat far away from home, I get a lot further away from home, and then when I'm coming back like this, I'm getting closer to home, okay? So the height represents distance from home. Then the slope at a given point is going to represent how fast I'm driving, right? How fast I'm going away from home or towards home. So you can think about this in two kind of ways. You can think about this as me driving a certain speed, speeding up, speeding up, speeding up, speeding up, slowing down, slowing down, slowing down, stopping, and then putting it in reverse and reverse, reverse, reverse until I get to this point. And that would tell a story of how I came to be this much further away from home than when I started, right? But another way to say this same story is, look, rather than driving like 10 miles an hour, then 20 miles an hour, then 10 miles an hour, then 0, then -10, I can just drive 15 miles an hour for the whole time and achieve the same result. That's a little bit of a convoluted way of saying it, but roughly speaking, this is the average slope of this curve from A to B is the same as the slope of this line which connects those 2 points. Okay. Any questions on this formula so far? Okay, so let's see how we can apply it. So here's a quick example. Let g of x equal this function, and we have a graph of this function. And what are we supposed to do? We're supposed to draw a line segment between points on the function where x equals 0 and x equals 3. So let's do that now. Here's x equals 0, and x equals 3. Looks like we're all the way up at 9. So this is the line segment shown here. Compute the average rate of change of this function over this interval. It's as simple as plugging into the formula. Average rate of change, in this case, is going to be f of, now b is always the endpoint on the right, okay? So it's always the endpoint on the right. But if you mix it up, don't worry, because if you make the top negative and the bottom negative, the negatives will cancel out and you'll end up with the same thing. So it's not a big deal to switch those up. But we're going to do f of 3 minus f of 0, and then we're going to divide by 3 minus 0. So in order to finish this, what we should do is take 3 and plug it into the function. Take 0, plug it into the function. Oops, it should have been g, huh? Sorry. So g and g. And what do we get? Well, 3 cubed is 27, minus 18 is 9, minus, if you plug in 0, you're going to get 0. And then we divide by 3 minus 0, and we get 9 over 3, which is 3. Okay, so the last part, I mean, what does it say? What is the connection between the line segment and the average rate of change? We've already discussed this. It's sort of the average slope, okay? It's the average slope as we go from 0 to 3 in x values is equal to the slope of this line here. Okay, so this is the definition of average rate of change. Some intuition behind it, and an example of how to compute it. Are there any questions so far? Yeah.
I just have a question about like how come we had to plug the 3 into the equation? How come we didn't just do 3 minus?
You mean at this part? Okay, so what we have to remember about g is g is a function, right, whose output depends on the input, right? So what I mean when I write g of 3 here is actually a different number. It's the number that I get if I take 3 and substitute it in here. So let me show you what that looks like. So that looks like g of 3, and then we write equals, and anywhere I see an x, I'm going to replace that with the number 3. So I get 3 cubed minus 2 times 3 squared. And 3 cubed is 3 times 3 times 3, which is 27, minus, and then this would be 2 times 9, which would be 27 minus 18, which would be 9. Does that answer your question? Okay. I wasn't sure if that was what you were talking about or not, but yeah, so that is how we got 9. Instead of 3, we have to plug into the function. But on the bottom, we just put 3 minus 0 because in the formula, it says f of b, so you need to plug b and a into the function in the numerator, but not in the denominator. All right, good question. Any other questions out there? All right, then let's work with a partner. What I'd like you to do is try problem 3. You can try like a couple of them on problem 3, and once you get the hang of it, if you feel confident, then try moving on to problem number 4, okay? And I'm going to be walking around. We'll take about 10 minutes, and I'll be around to help as you need help. So please do work with a partner if you can, please. If you need a partner, raise your hand, and I'll come help you out.
Well, I did see on it. Right. So now I'm gonna say.
What?
Yeah, I was like, oh, I only did A, B, and C.
I did A, C, B, I didn't do B, C cross. I only know that one, right?
So for the first
one.
Or at least I attempted to.
I don't whack it. You heard it. So what we want to do is
No, I'm just a little.
how do I figure out stop?
No, I have to read this like 14 times in order to understand the smallest part of it. It's like actually sad.
Y'all work together?
That's exactly what I was thinking.
I mean, that's technically like, how else are you supposed to?
I'm sorry.
I don't know. I can't really get off the top of my head though.
How's it going here?
It's going all right.
Okay.
Yeah, no, I can't.
Okay, right. I'm a little confused by this part. What's going on here?
27.8.
Oh,
27.8.
yeah, that's good. And then, yeah, so we're just really just plugging into the formula, right? So on the top, all we're trying to do here is just plug that in, right? Okay, looks like y'all are on the right track.
And then we just multiply that by 3.
Eight's always on the left, you go zero, right? So you go left, right. Yeah, -4 right? But it's even if you mess it up, way close, right? If you think of like rise versus if you were to go in the opposite direction, like negative rise over negative run.
There's no way
Yeah,
that's
so actually it's not to make sure that you get
There's just no way you're supposed to do that.
I don't understand how you make, I mean, unless you did like the range from 1 to 52 and then tried to do it like that, which I think like, you can't like.
Oh, right, you're already like, you're really poor.
Yeah, I don't know if it's right. I just divided it by 52. You guys do, so it's like 4. So you guys like did 2 right?
You did 2 before.
Yeah, I mean, it looks correct to me, right? I mean, if you want to think about it in terms of average rate of change, what you could say is,
Yeah, but like here.
look, you want to know how much she had spent at the end of the year minus how much she had spent at the beginning of the year, but of course at the beginning of the year, she spent 0. So you could rewrite this equation as 1450 minus 0 over 52 minus
So
0.
you guys do like
You see what I mean?
Yeah.
And that would be sort of like a average rate of change sort of a thing. Does that make sense?
Yeah, we did. And then we plugged them in.
Like for problem 4, did I do that too like stupidly? Like is there more to it than that?
No, I'm gonna reiterate that in a second.
Okay.
And that'll answer your question, I think.
We're just too smart.
Alright, does anyone need a little more time to work? Or would like a little more time to work? Okay, take about 1 more minute, okay? Alright, let's see here.
I'm not sure how to work.
Not sure about D. No, I mean, it looks good.
I got.
Yeah, no, I think this is totally fine.
I think
It's
that's
just a test,
like
like,
literally 1.1.
you know, treating very close numbers in certain contexts. Sometimes we're gonna treat them like this, and then later on,
Just take my time and learn
solve
all three
these
next
times
time.
like that.
Okay,
Does that
no,
make sense?
I feel like I did it the stupid way.
Well, I think actually
I just divided it by the 52.
Why
It was just 52 weeks in a year.
Amount of
And you
gas,
was like,
or sorry,
voted
amount of money
minus
spent on
0.
gas so far this year. Does that make sense?
well,
The time period is gonna be, let's see, it says the amount that she spends on gas each week. So it's on a weekly basis, but there's a difference
I
between
haven't gone to
describing
nap yet today.
amount
Dude, I'm
spent
wanting to this gym after this class. I'm gonna go back to it. I'm gonna fall asleep.
right? Because like, if I spend $100 a week on gas, right, my cumulative spending goes 100, 200, You know why? Yeah,
20 minutes
well,
of nap time.
time is always the independent variable, right? So time is gonna go on the horizontal axis because, right, so the horizontal axis will be time, so that'll be like how many weeks it's been. And then the vertical axis should be how much we spent, right? Because time is not gonna, time's gonna go forward whether we spend money on gas or not, right? Can I get to it in a second? Or just ask it if I don't answer it in the process of this explanation. Is that okay? All right. All right. Let's come back together as a group. So the first part I think is kind of just to give you some practice plugging into this formula, but that's really about all that it is, right? So here, what do we want to do? We just want to take g. Whoops. We just want to take g of 1 minus g of 0 over 1 minus 0, right? And if we do that, then we get 2 over 1, which is 2. Okay, likewise for all of these, all we're going to do is we're going to take the right endpoint. We're going to plug it into the function. We're going to take the left endpoint. We're going to plug it into the function. And then we're going to divide by the difference in those endpoints. So for this one, it would look like g of 2 minus g of negative 4, all divided by 2 minus negative 4, which would be 2 plus 4. Okay, and so on and so forth. Are there any questions on problem 3? I think I saw most people felt sort of comfortable with that after playing with it for a bit. Yeah.
For D,
For D.
you, so I got 2b squared minus 2a squared over b minus a.
Yep.
Do you get rid of, you cancel out the b and the a and then get rid of the squared on top of that?
Yeah, I mean, you could simplify. I mean, on an exam, okay, I will always specify whether you need to simplify completely or not. If you don't need to specify, or if you don't need to simplify completely, I'd be okay with this. But what could we do? We could simplify it a little bit, maybe, by taking a 2 out of the top, right? And then it'd be b squared minus a squared. And then on the bottom, we'd have b minus a. And then this is a difference of squares, right? Difference of squares can be rewritten as a product of b minus a and b plus a by factoring. And then you could write b minus a on the bottom, and you can cancel. You get 2 times b plus a. Okay, so if the problem said and fully simplify on the exam, then I would want you to do this part here, okay? If I say fully simplify, I need you to write the fully simplified version. Otherwise, I would accept something like this. All right, does that answer your question, Alex? Any other questions? All right, how about problem number 4? Well, it's a little bit strange, the way that this problem is worded, because, but here's what I think it's kind of going for, is, well, the average weekly gas expenditure could be described using average rate of change of total money spent from week 0 to week 55, or 52, Jesus, 52, right? So you could rewrite that average rate of change as, well, how much have we spent at the end of the year? That's $14.50. How much have we spent at the beginning of the year? 0, because we haven't got gas yet. And then we'd have 52 minus 0, okay? But my guess is most of you sort of switched straight to the end here, 1450 over 52. I think you probably went straight here and got to this point. So this is the average gas per week, right? So this is like dollars per week on average that are spent. So if nothing major changes, how much should Mary budget for gas for the next 3 weeks? How are we going to figure that? Yeah, we take 1450 over 52 dollars per week, and we multiply that times 3 weeks. The units of week and week cancel one another, okay, and we get a total amount of money, right? Namely 3 times 1450 over $52. Okay, so a little bit of a strange example, but yeah. Any questions on the second problem, problem 4? Stephanie, did we end up covering what you were talking about? You think so? Okay. Well, if you think of another question, you can ask after class. All right. So we're going to move on now to average velocity. And I'm not really going to say much about average velocity other than velocity is the rate of change of the distance function Okay, velocity is the rate of change of the distance function. So average velocity is going to be the average rate of change of the distance function, which would be, whatever, d of b minus d of a, d of a over b minus a. Okay, so nothing fancy here. Average velocity is just a specific application of average distance. So let me maybe draw an example. Average velocity is a special case of average rate of change, where the function that we are taking the average rate of change of is the distance function, because the rate at which my distance from an object is changing is exactly my velocity, right? The rate at which I am moving away from something is my velocity with respect to that object. So let me draw a picture here and tell you a story. It's not an exciting story. The story goes like this. This is my distance from home, and this is hours, and this is in miles. So let's say I start at home, i.e. at time 0, my distance from home is 0. And then I drive 30 miles in 1 hour. Okay? And then I drive a little bit slower for a while after that. I drive an additional 10 miles over the next hour. Okay, then we can ask the question, what was my average velocity for the first 2 hours? The first 2 hours. Okay. Well, all I'm going to do is apply the average rate of change formula to the distance function. So this is going to be d of 2 minus d of 0 divided by 2 minus 0, right? Which would be 40 over 2, which would be 20. Okay, and what are the units of the top? The units of the top are miles. The units of the bottom are hours. So the units at the end of the day, the average rate of change is 20 miles per hour. So this is a very simple and boring story. What it says is, I drove 30 miles an hour for an hour, and then I drove 10 miles an hour for an hour. That's the same as driving 20 miles an hour for 2 hours. Does that make sense? Yeah.
Would you normally put it as like 10, or would you put it as 40?
Oh, sorry, yeah, so it should be 40. Yeah, all the time you're going to notice I make these sorts of mistakes when I'm lecturing, just because I'm saying something which is different than what I'm writing, which is harder than you might think. So yes, if you see me make a mistake like that, then just raise your hand or yell out or something, or have a conniption. Okay, any questions on this very boring story? Okay, but you can see how this could also describe something a lot more complicated. Like, first of all, it doesn't make sense for me to be driving 30 miles an hour and then suddenly be driving 10 miles an hour, right? What would I have to do? I'd have to press on the brake and slow down continuously first. So probably this graph would look more like this. It'd have a nice smooth transition between those two. And now it's a totally different question of like, okay, well, if we have a smooth transition between those two, how are you going to say the average of how fast you were going? Because at one moment you were driving, 29.951 miles per hour, and then instantaneously the next moment you're driving 29.950 miles per hour, right? How are you going to average all of these things up? Well, it's a little bit more complicated than that, but if we say where we started and where we ended, we can say that the average of the middle period is equal to the slope of this line. Does that make sense? Okay. Any questions on that before we move on? All right. Doesn't sound like there are, so let's talk about relative change. And by let's talk about it, I mean I'm going to talk about it for like 2 minutes and then we're going to move on to something else. Okay, so relative change, I claim that you all already know what relative change is. If you have ever bought something on sale, right? If you go to the Gap or to the Hollister or the wherever people shop these days, or just online or something, I don't know, and you see 20% off, what they mean is whatever the original price is, take 20% of that and remove it. That's our new price, right? That's all that relative change is. So we want to describe this in the following way. Well, the relative change from time A to time B is just whatever is the new price minus the old price divided by the old price. Okay, so let's do a really quick example. $100 t-shirt, really expensive t-shirt. Now it's $80. You know in your brain already what is the percent off, right? But let's verify. We're going to do 80, right? 80 minus 100, because 80 is the new price. We subtract from that the old price, and we're going to now divide by the old price, which would be 80 minus 100, which is negative 20 over 100. That gives us 0.2 or 20%. Okay? Actually, it gives us negative 0.2 or negative 20%. Okay? So that's the relative change from the original price to the new price. Okay? And whether we're negative or positive means off or markup, right? Okay, so this is just a formula. So let's see one other thing. So okay, let's say that in January 2017, YouTuber has 1.5 million subscribers. And today they have 2 million subscribers. What is the relative change? Well, all we're going to do is the new number minus the old number and divide by the old number. And we get 0.5 million over 1.5 million. Cancel, cancel. How many times does 0.5 go into 1.5? 3. So this is 1/3. Or if you want 0.33 or 33% increase. Okay? New number minus the old number, divide by the old number. Any questions on relative change? All right, I know this is kind of boring with just me talking at you, but we're going to move on to, well, we're going to do a couple more concepts of me talking and then close, or well, then we'll have the quiz. So the next thing I want to talk about is concavity. And concavity, well, you might know about concavity within the context of mirrors, okay? So if you are a person who does their makeup, you might have a convex or a convex mirror, which allows you to see your face more clearly. Or if you drive a car with a really big blind spot, you might have a concave. No, concave? Whatever. You might have a mirror on the side of your car, right? Which is sort of bulbous in this way that allows you to see more. Okay, so what is concavity and convexity describing? It's describing like the curvature, okay? Whether it's curving in one way or curving in the other way, okay? That's what concavity is about. So for now, well, at some point we are going to describe what concavity is mathematically, but for now I'm just going to describe how to recognize it visually, okay? How to recognize it visually. Okay, so I'm going to do a table here. Okay, if the graph looks like this, whoops, if it looks like this, or if it looks, okay, why don't I use a different color? If it looks like this, or if it looks like this, then we call this concave up. And I like to do a big U for the up, because guess what? The U in the word up is concave up. Okay? Concave up. Roughly speaking, it means that we're bending upwards. As we move from left to right, we are bending upwards. You can think about it as if I was driving a car. Wheel 1, 2, 3, 4. Okay, if I was driving a car in this direction, I'd be turning my steering wheel to the left. Yeah, I'd be turning my steering wheel to the left if I was following this thing from left to right. So if I'm driving like this, right? If I'm driving in this direction, I'd be turning my steering wheel to the left. That means we're concave up. Okay, and next we have ones that look like this. Okay, not so good at drawing today. Okay, pieces which look like this, we call them concave down. And I like to do the N real big because the N in the word down is concave down. Okay, so all I'm asking you right now is to visually identify whether something's concave up or down. Okay? And we'll talk more about it later. So let's take a look at this picture here and talk about when are we concave up or concave down. Well, as we go from A to B, what do we think? Concave up or concave down?
Down.
Concave down. How about going from B to C?
Down.
Still down. Okay, here's why. Think about me driving a car. My car is really wide and really short. But, okay, if I was driving a car and this was like a top-down thing, I'm turning my steering wheel to the right. Just because I get to this point, I'm still turning my steering wheel to the right for this section, okay? This still looks like the letter N, kind of, okay? How about from C to E? Would I have changed the direction of my steering wheel?
Yeah.
Yeah, I would. I'd be turning left now. Okay, so I think from A to C, we are concave down. And then we're concave up for a while. When do I stop being concave up?
E.
Yeah, E is where I stop being concave up. It's where our curvature switches from being this kind of turning to the left to this turning to the right. Okay? So I would say C to E, we are concave up, or convex if you want to use the word convex. And then we're concave down again till G, right? So we'll also say not only A to C, but also E to G. Okay, so just because we're going up or going down doesn't have anything to do with the concavity. It's about what is the curvature. Okay, what is the curvature? All right. Any questions on concavity? Okay, so this kind of goes together with we could fill out even another section of this table. Let me increase these a little bit here. And I'm also going to write that these are decreasing and these are increasing. Right? Because as we move left to right, we go up. But we are also concave up for this one. Here we're going up, but we're concave down. Here we are going down, but concave up. And here we are going down and concave down. Okay? So it's a question of, these are sort of two different concepts, whether we're increasing or decreasing, and whether we're concave up or concave down. Questions on any of that before we move on to the next section? All right, then I'm going to move on. Okay, so the next section, 1.4, is all about business, which a lot of you are business majors or in the business school at least, doing marketing or entrepreneurship or something. So that's what this class has a major component of. So with respect to that, we're going to be coming back and talking about three functions over and over and over and over again. And those functions are the cost function, which represents how much money your company has to pay in order to accomplish a task. The revenue function, which is going to describe how much money you are paid for either a product or a service. And then there's the profit function. But can anybody who's a business-minded individual explain to me what is the difference between profit and revenue? Exactly. Profit is how much you put in your pocket after you factor in your costs, right? After you factor in your costs, okay? So if I spend $1,000 to buy something and then I sell it to Braden for $1,000, how much profit did I make? I made $0, right? That's my profit. My cost was $1,000, my revenue was $1,000, but I didn't make any profit, okay? So that's the difference between cost, revenue, and profit. So let's write them down. C of Q is cost of producing Q units. Cost of producing Q units of good or service. Okay? All right, so then revenue is amount charged to consumer for Q units, which is not the same thing as the profit function, which, by the way, for the profit function, for whatever reason, the book likes to use the Greek letter pi for the profit function. So we do pi of Q, but you can think about it as like being P of Q, basically. Okay, pi of P, profit. All right. So pi of Q is going to be given by, of course, however much money we charge minus however much money we had to pay. Okay, so these are the basic cost, revenue, and profit functions. And what we're going to consider for now are linear cost, revenue, and profit functions, okay? Later we're going to talk about curvy ones, but for now we're just going to say, look, more goods equals more expense, more goods equals more money coming in, and then of course the difference between two linear functions is going to be, again, a linear function. Okay? So that's cost, revenue, and profit. The last thing I want to talk about for those is what is the notion of marginal cost, revenue, and profit. So marginal cost, revenue, and profit describe the rate of change of these three functions, okay? So for now, since we're considering these functions to be linear, the marginal cost is just the slope of the cost function, okay? Just the slope of the cost function. And the marginal revenue is the slope of the revenue function. The marginal profit is the slope of the profit function. Okay, so let's see an example of marginal cost in action on problem 1. Okay, goods R Us has a cost formula of C of Q equals 9,876 plus 0.5 Q to produce Q goods. Okay, so what is their fixed cost and what is their variable cost? So fixed cost refers to a cost that does not change depending on how many units you produce. Okay, so think the price of your brick and mortar establishment or your factory or something like that. Whereas if you're producing a good, the variable cost is going to be how much you need to provide, like the supplies to make one good, right? Okay, so let's see here. So 9,876, that's the fixed cost, which could represent maybe the toy store price. I guess it's goods R Us, it's not toys R Us. But anyways, you get the point. This is like the cost to buy the store. One-time payment. Then 0.5 is what we call our variable cost. And I would say that is cost of making one toy. And of course, this is a linear function, and the marginal cost is just going to be the slope of that function. So what is the slope of this cost function? Yeah, it's 0.5. So the variable cost is actually the same as the marginal cost. All right, any questions on that? We're going to talk a lot more about, yeah.
When would marginal cost and variable cost compare?
Pretty much never. They're just two different ways of saying the same thing, I think. Yeah, two different ways of saying the same thing. All right, if no other questions, then we'll stop there for today and do the quiz. So please clear your desks. If you're wearing a hat or a hood, please put it down or put it backwards. If you are having a cell phone, please put it all the way into your book bag. All of the papers go away. The only thing you need on your desk is a pencil. Yep. Oh yeah, go ahead. If you are wearing an Apple Watch or a smart device anywhere else on your body, like an Apple ankle bracelet, then please take it off and put it all the way into your book bag. Raiden, hat backwards.
Oh, well, then.
All right, everybody all set? Okay, I'm gonna pass these out, but please leave them face down on your desk until everyone has one, so that everyone gets the same amount of time. Can you put your phone away, please? Yeah, actually, go ahead.
You guys will get something.
Okay, does everybody have a quiz now? Okay, you may begin.